Good afternoon, everyone, and welcome to the semi-finals of this year's virtual 3-minute thesis competition. My name is Elizabeth Mamali, and I'm the Postgraduate Researcher Development Officer for the Bristol Doctoral College at the University of Bristol. For those of you unfamiliar with a 3-minute thesis, the competition challenges postgraduate researchers to present a compelling spoken presentation on the research topic and its significance in just 3 minutes. An 80,000-word thesis would take 9 hours to present. So how will our presenters perform in just 3 minutes and with the aid of a single slide? Our semi-finalists have already delivered their presentations to a judging panel, and they're anxious to hear the outcome. This will be announced by our industry judge, Abhi Sankaran, who is the Head of Innovation and Partnerships at Science Creates Incubators, at the end of today's broadcast. 6 of today's competitors will then have the opportunity to take part in the university's finals next week, which we hope you'll join us in attending and use your opportunity to vote in the People's Choice category. Thank you again for joining us this afternoon, and best of luck to all of our competitors.
Who among you would be willing to give me your credit card information? I expect it's not many of you. But when's the last time you thought twice about giving that information to Amazon, Deliveroo, or PayPal? These companies depend on you trusting that your details are safe in their hands. It turns out the best guarantee for your data is to say that we don't know of anyone that can steal it yet. The problem is, blueprints are being drawn right now for machines that can do exactly that. Using the spookiness of quantum mechanics, these computers go far beyond what we're prepared for. So what happens now? Is this the end of online safety? Encrypting your data is like locking your car in many ways. Like car doors, encryption uses a key to lock your data so that it's safe in public. It can then be unlocked or decrypted using a key whenever access is needed. It is therefore crucial that only trusted parties should have the keys to something so valuable. Otherwise, in both cases, someone else will soon be driving a car that you just paid for. The encryption keys we use now are just random numbers. Their security comes from the near impossibility of guessing the right number. But in theory, specialized computers can be made with the power to remake these keys from their locks and then pick them. This is done by harnessing the strange rules that govern single particles at the scale of atoms. We call these rules quantum mechanics. These quantum computers can also be used to help design better drugs, or even help with climate change. So billions of dollars are now being invested into making them a reality. My research aims to build a quantum solution to this quantum security threat. One of the spookiest and most widely known quantum laws is that simply observing a particle is enough to change it. So by sending information using single particles of light, we can tell if someone's listening in. That's because just by seeing it, they must have changed it. In this picture, from green to red. We can use this to build locks and keys that can't be picked even using a quantum computer. But these single particles are fragile. They can't survive the hundreds of kilometers of optical fiber that we currently use, and this severely limits an otherwise powerful solution. Our idea is to do this from a satellite. Crucially, you can see in this picture that the atmosphere is relatively thin. So the signal mostly travels through the emptiness of space, where there's nothing that can interfere with it. We're using this to unlock quantum safety at global distances. So the only question for us now is, can we do this before it's too late?
Imagine that one day you were given a key that gave you access to reams of hidden, unpublished research material that could challenge our prevalent views of history. At the beginning of my PhD, I was given that wonderful gift, access to an entire archive of meticulous, painstaking research typed on a typewriter by a local historian and Brecon nun, Sister Bonaventure Keller, who had recently died aged 96. She'd had an unwavering passion to tell the story of Brecon's forgotten 18th and 19th century theatre history, and over several decades had collated a huge archive of material which she stored in her bedroom at the convent. She tried to write it up and publish it, and was still trying to do so right up to her death, when she had failing eyesight and poor health to contend with. She never finished. And here is where I come in. My research has been funded in her memory to finish what she had started. So how am I doing this? Well, my role as archival resident is a key part of my methodology. I live in Brecon and so have the wonderful privilege of being able to immerse myself in the history. A trip to the supermarket becomes an opportunity to walk past the building which housed the town's 18th century theatre, a building I previously never knew existed. A bike ride transforms me to Maria Williams, an 1826 patron who travelling into town on her horse-drawn carriage. Her unpublished diary reveals glimpses into the lives of the women who funded the theatre. This project is important as retelling forgotten histories in the 21st century enables us to reconfigure and challenge the dominant history narratives. In this case, challenging the London and male-centric narratives of 18th and 19th century theatre history. I can focus on the women theatre makers in a small town whose part in theatre's history has been largely forgotten. To ensure this project has as big an impact as possible, I'm exploring ways of engaging the local community through the delivery of a heritage-funded lottery project, which includes community theatre performances, interactive maps, educational resources. The idea is that these stories become enshrined, retold, and remembered. My hope is to find a model of practice where forgotten histories are celebrated and moved from the confines of academia, or a nun's bedroom, to have meaning and purpose for communities. Thank you.
Thank you, Jen.
Okay, raise your hand, anybody here who's ever been affected by pregnancy or childbirth. That's right, it's a trick question. Everyone would have their hands up. When I was awarded my PhD, my friend said to me, "Nance, women have been giving birth for millennia. It's the most natural thing in the world." But just because something is natural does not mean it's not complicated. In fact, around 40% of pregnancies can experience some kind of complication. This can be the mother having very high blood pressure, high blood sugar, the baby being born too large, too small, or simply too early. These don't just have very bad health consequences at the time, but also going on into the future. But it's not all doom and gloom. We do actually have effective treatments for many of these complications. For example, antihypertensive drugs for high blood pressure or hypoglycemic medication for high blood sugar. However, the issue is we do not know which women will experience these complications, often until they have symptoms, and by then they're often already very ill. Therefore, we do need to know which women will be at risk of these so we can tailor their antenatal care accordingly. This has the added advantage of reducing unnecessary intervention in low-risk women. At the moment, we do have ways of assessing risk of a pregnancy complication, but these are quite basic risk factors. So for example, the mother's age, her ethnicity, maybe even her body mass index. However, these are all quite blunt instruments. Many women who go on to have a complication were not classed as high risk by any of these risk factors. A very good predictor of a pregnancy complication is a previous pregnancy. So for example, if a mother previously had a preterm birth, she is at higher risk in her next pregnancy. However, for obvious reasons, we cannot use that in women who are on their first pregnancy, who are most at risk of a pregnancy complication. And this is where I come in. My PhD is all about improving the prediction of pregnancy complications. So in my PhD, we use a snapshot of maternal health from blood samples. You'll have heard the word metabolism 1,000 times in your life. We actually have products of metabolism in our blood. You'll have heard of many of them: carbohydrates, steroids, sugars. These can tell us a lot about ourselves, our genetics, and also our environment. So for example, our diet, whether we smoke, whether you took paracetamol this morning so you're a bit hungover, which you shouldn't be because it's a Wednesday. So in my PhD, we use these blood samples to try and improve the prediction of pregnancy complications. So we had blood samples from thousands and thousands of women of different backgrounds, ages, and ethnicities. My results show that these do actually improve the prediction of certain pregnancy complications compared to the basic risk factors that we touched on before. This means that potentially in future, these could form part of routine antenatal care, where blood sampling is already very common. So this is why I say what you don't know can hurt you. Thank you.
Does temperature drive marine anoxia? Marine anoxia is a marine state without oxygen. Today, the temperature is increasing, and one of its impact is the oxygen loss from the ocean. In fact, 2% of diesel oxygen have lost since 1950 from the ocean, and under business as usual, this could increase from 3 to 4% in near future. This is significantly harm marine species, our food supplies, as under warm temperature, the oxygen minimum zone could expand. The oxygen minimum zone is a dead sea, it's a dead zone for marine species, as no oxygen can survive in this zone. In my PhD, I'm studying the past oceanic anoxic events, OAEs, to reconstruct the paleo sea surface temperature and its link with the oxygen minimum zone expansion by looking and tracking the anoxia in the water column. I employ biomarkers and molecular fossils, which is organic compound of lipid membrane, as a signal from the past. Biomarkers are very useful for 3 reasons. 1, they show adaptation to the environment. Secondly, they are species specific. For example, archaea that can be used to reconstruct sea surface temperature. And third, they preserve over millions of years. Using biomarkers, I find that the Equatorial Atlantic Ocean was extremely hot at 41 degrees Celsius compared to modern of 29 degrees Celsius. In fact, the rising of anoxia have developed to the surface of the ocean, coupled with the oxygen minimum zone expansion. I argue that massive release of atmospheric carbon dioxide have induced the sea surface temperature to be high and intensify the continental weathering, which subsequently increased the primary productivity at the expense of oxygen concentration. Consequently, the black shell indicate mass extinction. Today, atmospheric carbon dioxide and temperature are both rising. Let's reduce our carbon footprint and save the ocean. Thank you.
Have you ever had a blood test? Do you know which tests were done and why? I'm a GP. I request blood tests every day. In my PhD, I've been studying tests called inflammatory markers. These are non-specific tests for inflammation in the blood, which can be used to help diagnose infections, autoimmune conditions, and sometimes cancers. I've been interviewing doctors and patients about their expectation and understanding of these tests. Quite often, patients don't know which tests they've had done and why, and this means they often don't understand the meaning of their results. Doctors are aware that test results might not provide the clear-cut answers which patients are hoping for. They know all tests can lead to false positives and false negatives, but doctors rarely discuss this with patients openly. To explore how often these false positives and false negatives occur for inflammatory markers, I've looked at the anonymised electronic health records of nearly 200,000 patients. To explain my results, let's think about your smoke alarm at home. Most of the time, there's no alarm and no fire. Good news. When I studied these tests, I found a similar thing. Most people, shown in green, had normal results and no disease. We call this true negatives. If a fire starts, the alarm should ring. With tests, we expect the same. When you have a disease, this should be picked up with an abnormal test result. We call this true positives, shown here in yellow. But just like your fire alarm, blood tests aren't perfect. Sometimes an alarm goes off when there is no fire. Perhaps you left the toaster on. We call these false alarms a false positive, shown here in red. This is an abnormal blood test, but without disease. This happens surprisingly often for fire alarms and blood tests. Sometimes we get a fire, but our alarm fails to go out. Perhaps the batteries have run out. We call this a false negative. Our test was normal, but we do have disease, shown here in blue. As you can see, these inflammatory marker tests aren't perfect, and I hope by better understanding the limitations of these tests, GPs and patients can make measured decisions about when best to use them. I hope they can share these decisions so that patients have a better understanding of which tests were done and why, and what the results mean for their health. We need to talk about testing.
I remember the first time I was prescribed antidepressants. It came after a week-long series of panic attacks where I felt like the walls were melting away around me. And the only thing I could see, hear, and feel was a sense of dread sitting in the pit of my stomach. So I called a mental health nurse and she prescribed me sertraline, a type of antidepressant. I looked at the packet and thought, okay, but what will happen to me if I end up taking these? And what will happen to me if I end up taking these for a really long time? My research is about what we do when people get sad, what we do when people get so overwhelmed that they feel like they can't cope. And particularly, I'm interested in what antidepressants do for the people that take them. The UK has one of the highest rates of antidepressant use in the world, with 17% of people taking them in 2018. That's 7.3 million people. Many types of antidepressants work by blocking the reuptake of serotonin, a key brain chemical involved in various different functions, including mood. But what we don't really know is how long we should block the reuptake of serotonin for, or what happens if we use this mechanism for years and years. Clinical trial data suggests that antidepressants work by reducing the symptoms of depression over placebo. But what if those trials only track people over a period of months? What about people who end up taking antidepressants for years? Do they feel better? Do they still suffer side effects? At what point do they consider themselves recovered enough to stop? And what will happen to their symptoms when they do? My PhD uses data on antidepressant use from a large data set containing thousands of different people. And I'll be using different types of data analysis to study the health outcomes of these people, looking to areas such as cognition, genetics, mood, rates of recovery, and physical things like weight changes and sexual function. A type of data analysis that I'll be using is called machine learning. And machine learning allows us to see patterns in data over large-scale data sets. Machine learning can help us understand the similarities between people who start to feel better after taking antidepressants. But crucially, it may also help us understand the differences between those that recover and those who end up responding badly. Perhaps gender plays a role, or age, or there are genetic factors which make someone more likely to experience bad side effects or suffer from withdrawal symptoms. We need to know more about how to safely administer medication over the long term, so patients are equipped with the right tools to manage their mental health challenges. Let's make sure that we're asking the right questions to ensure that all patients really understand what antidepressants do. Thank you.
Have you ever been in love? If so, then you know the power of peptides. or more specifically, a single peptide known as oxytocin or the love hormone. Determining how you feel is just one role that peptides play. And inside you right now, a plethora of peptides are working away to ensure that your body functions just as it should. So we know peptides, though small, are mighty. But can a single peptide tackle global crises of food security and antibiotic resistance? Well, when a peptide's function is unknown, the possibilities are endless. But what is a peptide? At the top of the slide is how scientists represent these molecules. And I don't know about you, but this doesn't really mean that much to me. Instead, it's far simpler for me to imagine peptides as being made from building blocks. So something like Lego. With Lego, depending on how you arrange the blocks, you get something with a different function, whether that's a house, a bridge, or something you can't quite place. And it's the same with peptides. Different arrangements of the building blocks of peptides result in different functions, some of which are equally unknown. So where do we start to look for these peptides with unknown functions when every living thing produces them? Well, perhaps we should turn to fungi. And why fungi, you ask? Well, we know that they can change the world because we've seen them do it before with the discovery and application of the antibiotic penicillin, revolutionizing medicine and extending human lifespans. So why couldn't they do it again? And why should their power be limited to antibiotics? Though an incredibly useful power for humans to harness, human suffering doesn't always come from human disease, but rather plant disease and plant pests that steal food away from us. That's why in my research, I'm looking at a peptide from a global wheat pathogen called Zymoseptoria tritici, using plant inoculations and insect feeding studies to determine if the peptide is involved in plant disease, or equally, just as we want to protect our food from this fungal competitor, the fungus may use the peptide to protect its food from animals, including us, by poisoning it. So what are the implications of this? Aside from making a pretty good PhD thesis, there are some real applications here. A potential novel antibiotic, a target for breeding wheat plants with resistance to the fungus, or even a new anti-feedant effective against pests. We could simply sprinkle the peptide onto our crops to make them distasteful, as a kind of anti-salt, if you will. I'm only at the beginning of my investigation, but by looking at similar peptides with similar building blocks, I'm able to see that the anti-salt theory is the most likely. But I still wouldn't place any bets just yet. There is, after all, a kingdom of possibilities. Thank you.
Did you know that all the stars, planets, and even that cute hamster you saw on the internet last week makes up just 5% of the universe? To describe this 5%, we humans have created an elegant model called the Standard Model of Particle Physics. This model defines the basic building blocks, the fundamental particles, and how they interact with each other. Although this model exceeds our expectations in many ways, there is a problem. The Standard Model of Particle Physics predicts that the universe should not exist. But since we definitely do exist, there is something wrong. 13.8 billion years ago, just after the Big Bang, matter and its opposite antimatter were created in equal amounts. Our model predicts that through subsequent interactions, matter and antimatter should have destroyed each other, leaving nothing behind. But observations show that 1 in a billion matter particles survived, creating the universe we see today. In other words, this means that there is a difference between the behavior of matter and antimatter, and it is very puzzling. In many ways, it's unfortunate that we don't have a time machine to go back in time and study the Big Bang directly. So we had to compromise, and we built the Large Hadron Collider. Being the largest machine built by humans, it is a 27-kilometer ring, 100 meters underground, where protons are accelerated to the near speed of light and collided with each other. These collisions create a lot of subatomic particles, which undergo a process called particle decay, where they transform to less massive particles. On the picture on the top right, you can see these particles going through the detector, which identifies and measures their properties. I am interested in one such decay, where a particle called a bottom quark transforms to a strange quark along with a pair of electrons or muons. I know what you're thinking. Physicists can get very creative with names, but not worrying too much about the bottom or strange quark, I draw your attention to the pair of electrons or muons created in this process. Electrons, as you may know, is the carrier of electricity, but muons are just a heavier version of electrons and expected to behave very similarly. Over many such decays, equal amounts of electrons and muons are expected to be produced. But recent measurements show that more electrons than muons are seen. I am trying to understand where this difference comes from by comparing these decays to our predictions. If my work confirms that these differences are truly something new, it means that there's another fundamental force in nature, along with more undiscovered particles. Understanding these will help us explain the difference we see between matter and antimatter in the universe. This is a very exciting time for particle physics. The experiments at the Large Hadron Collider are undergoing major upgrades, and the next decade will be gaining more insight into the mysteries of the universe. Thank you, and stay tuned.
From the dawn of humanity, our ancestors have looked to the stars and been fascinated by the night sky. Since then, we have come a long way, and decades of pop culture media have promised us a future where human beings are a spacefaring civilization. From settling on other planets, taking vacations on moons, to traveling to the very edges of our solar system, movies and books have captured our imaginations. However, before we make this fantasy a reality, there are some very fundamental technical challenges which we must overcome. One of these main challenges are the materials that we use for space applications. You see, here on Earth, we have been great at building large-scale structures capable of surviving for long periods. Just look at the pyramids of Giza. However, even with all these advancements we have achieved, these same materials are not suitable to be used in space. When they are exposed to the space conditions, they do not have the same durability as they do here on Earth. Even the materials that we use for satellites and spacecraft design today are very expensive and deteriorate quite fast. Therefore, my PhD is focused on innovating new composite materials to be used in space applications. To understand better what a composite material is, picture a lasagna. In a lasagna, you have the lasagna noodles and you have the filling layered in between. Similarly, in a composite material, instead of the lasagna noodles, you will have the fibers, and instead of the filling, you will have a material called matrix. When you combine the matrix and the fibers, you end up with a much stronger material, which is still lightweight. In my research, I have developed a new type of matrix, which when exposed to the harsh conditions of space, it creates a self-protecting layer surrounding the whole composite and making it even more resilient. Over the past 2 years, we have been testing this material in the lab by artificially recreating space conditions and testing the materials at small scale. However, even the results have been very promising. There are some other factors from space exposure that we cannot account to be in the lab. Therefore, we will actually be sending some of these materials to be tested in the International Space Station. So, if we're successful in testing these materials, we will not have only the composites required to build satellites and spacecraft, but we will actually have large structures. Imagine a hotel in Mars, which you can visit over the weekends, or imagine a school trip to the moon. With this new technology, we're becoming closer to actually making the transition from merely looking up at the stars to actually living among them. Thank you.
What is quantum mechanics? Around 100 years ago, our understanding of the world was revolutionized when we discovered that the maths that tells us how very tiny things behave is different to the maths that tells us how you and me-sized things behave. That's all that quantum mechanics is. It's the maths that governs how the unseeably tiny behaves. But when an enormous number of tiny subatomic things called electrons all act together, quantum effects can emerge into our world. Why does a magnet stick to your fridge? Because of quantum mechanics. Now, in my opinion, the greatest tragedy in all of physics, all of science, is that we may know the quantum mechanical equations that would tell us all sorts of fascinating things about the electronic and magnetic properties of every possible material, but we don't actually know how to solve those equations without making approximations. In my PhD, I've been testing different approximations by looking at something called a Fermi surface. Every metal has one. You can't see the Fermi surface with your naked eye. It exists in a reciprocal space to the one all around you. But it's a real thing. And with the right equipment, you can actually measure it, which is crucial for my research, because I've been comparing the shapes of the actual Fermi surfaces of different materials to ones that have been calculated mathematically through all sorts of different approximations to help us figure out which approximations work better for which materials and why. Think, entire eras of human existence are defined by the materials that were available to us to use at the time. The Bronze Age, the Iron Age, the Silicon Age. My hope is that by better understanding how best to approximate the mathematical quantum mechanical equations that tell us how materials behave, my research will contribute in a small way to the discovery and development of revolutionary new materials that will define the next era of human civilization.
Around 6,000 years ago, a monumental change was about to occur in Britain. If we could travel back to that time, we would see a very different Britain to today. One almost entirely covered in forest, where wild deer roam the land, and the small number of humans who lived here lived nomadically, surviving through hunting, fishing, and gathering. But fast forward 300 years or so, and a very different picture emerges. Trees have been cut down to make way for crops. People are building timber houses, and herds of cows and sheep graze in the brush. Farming has arrived in Britain. Now, farming didn't originate in Britain. In fact, there were farmers living in northern France for around 1,000 years before they arrived on Britain's shores, and farming practices had been sweeping across Europe for many thousands of years from their birthplace in the Middle East. So how do we actually know all of this? Well, archaeologists study traces left behind by humans to piece together what happened in the past. And one of the most important tools for an archaeologist is radiocarbon dating. Radiocarbon dating is a way of telling how old something is, provided that it was once alive. Things like bones, wood, even individual seeds can be radiocarbon dated. Do this enough, and you can get a picture of the timings of past events. For instance, it's how we know that in Britain, people were living as hunter-gatherers around 4000 BC, but as farmers by 3700 BC. But what was going on in those 300 years? How did farming get to Britain? These are questions that have puzzled archaeologists for decades. And one of the biggest obstacles to understanding this period is a lack of good radiocarbon dates. Suitable materials are scarce, as plants and bones tend to decay over time. One thing that doesn't decay, and that archaeologists find a lot of though, is pottery. Unfortunately, pottery itself cannot be radiocarbon dated, as it was never alive. However, when these pots were used for cooking, fats from the food would get absorbed into the walls of the pot and preserved there. Using a newly developed method, we can now extract those fats, which come from meat and dairy, and radiocarbon date them. This means that we are dating the use of the pot, and it opens up exciting new avenues for studying the past. My research, for instance, is using this new method to radiocarbon date the earliest pottery in Britain, pottery used by those first farmers to live here. This will enable a better understanding of how farming arrived in Britain.
Thanks, Abby, for your verdict, and thanks everyone for attending today. Remember to visit the University of Bristol Facebook page at 12:30 p.m. next Friday to watch the fast-paced final and help choose this year's People's Choice presenter.
Okay, so hello everyone. My name is Dr. Abhi Sankaran, and I am the Head of Innovation and Partnerships at Science Create. I had the pleasure of judging the 3-minute thesis semifinals. I just want to thank all the participants for taking the time and effort for preparing. It was a very close competition with a number of outstanding speakers. We would like to nominate the following 6 to the finals: Jessica, Holly, Rosie, Lakshan, Myra, and Isabel. Congratulations, you will be put forward to the final round. I want to again thank you everyone on behalf of the judging panel. Thanks.